We're going to look at conditional probability in this video. Now, conditional probability says that something has already occurred or something will occur, and you just want to find a proportion of it. So for example, if you know that out of 3 coin tosses, you definitely know that one of them's ahead, what's the probability that the next one's ahead? Okay, so that's what conditional means. All right, the table shows that the results of a survey of 100 people aged between 16 and 29 about their preferred choice of food when eating at a cafe. One person is selected at random from those surveys. Identify the event and use the table to calculate. Now, although there's a formula written here, you don't have to use it, okay? You do not always need to use it. You might then ask, why is that? Well, I'll just do some samples and you'll see what I mean. Okay, A, probability of M intersection V. So M is here, V is here, the intersection where they cross over is that one, so it's 18. Out of a total, which is 100. Alright, B. For B, we have M given that they're vegetarian. Now, here's what I'm saying, you don't necessarily have to use a formula. Out of the vegetarians, which has 43 of them in total, we have 18 of those who are male. See how I didn't use a formula? If I was to use a formula, what I would be doing is I would do 18 over 100, as of the first one, times, divided by 43 over 100, because we want the intersection of it divided by the other one. So you don't always have to use a formula. If you're given a table especially, quite often you can actually just read it and see what it is. Okay, so the next one, we want non-vegetarians for females. So we have 44 females in total, written right there, and the non-vegetarian females are here. So it's 19 out of 44. Okay. Part D, the probability of getting a vegetarian is 43 out of 100. You can also have a multiplication property. This is just rearranging it. So probability of B given A is the probability of the intersection of B and A over A, right? If I multiply that over, I get the formula on the left here. However, you might notice that the A and the B switched around. That actually doesn't matter. A intersection B is the same as B intersection A. Alright, the probability of A is equal to 0.6. A given B is 0.6125. B complement is 0.2. We want the probability of A intersection B and the probability of B given A. Alright, so let's follow the order of what we need to work out. Let's work out probability of A intersection B. If you have a look on the one above, A intersection B is probability of A times the probability of B given A. However, if you have a look on the top, we're not given that, right? So we can't use this one. So let's try the other version. And all you have to do is switch your A's and B's around, because remember they're the same. So we want probability of B times probability of A given B. So we have A given B, which is written on the top, 0.6125. However, we need probability of B. If you have a look here, B complement is 0.2, so that means probability of B must be 1 minus 0.2, which is then 0.8 times 0.6125. And then from here, you just put in the calculator, and you should get 0.49. Okay, 3 girls each select 1 ribbon at random, one after the other, from a bag containing 8 green ribbons and 10 red ribbons. Now it's implied that this one, that there is no replacement. If it does say with replacement, they'll tell you with replacement. Otherwise, it's usually no replacement. Okay, what is the probability that the first girl selects a green ribbon and both the other girls select the red ribbon? So first one, we want a green one, where we have 18 in total, so it's 8 out of 18. And the second one and the third one are red ribbons, so we have 10 at the start. However, we've selected one of the green ones, so now we have, oh, not 19, we don't add more, we subtract one, 17. And then we have 9 out of 16. Then doing some multiplications, 1, 2, 5, 1, 1, 2, we get 5 out of 34. Okay, probability tree diagrams. If you have a look, first one was to be A, then probability of B given A, and then we will get outcomes A intersection B. Yeah, it's pretty straightforward to read from here, so I'll just let you guys have a read of it. Alright, so this one talks about different chocolate centers. So you have 6 soft and 4 hard. Now, there's also this ith selection thing. What this tells you is what number they are selected at. So if you have a look at this first one, the one's probability of H2 as 1, what that then means is the first one is soft, and then the second one is hard. So probability of hard and soft over the probability of it being soft on the first one. So soft on the first one, we have 6 out of 10, because there's 10 in total, if you read the top. And then for it to also be hard, we then have 6 out of 10 times the hard center, which is 4 out of 9. Now be careful, because 4 out of 9, because we've eaten one of them, it's not out of 10. Construct a probability tree diagram to illustrate the possible outcomes. So we have hard, soft for the first one, and hard, soft, hard, soft. Now always write down your probabilities. For the first one to be hard, you have 4 out of 10, or in other words 2 out of 5. You should try and write it simplified whenever you can. The other one is 3 out of 5. Then we've eaten one of them, so out of 4 hard, we're left with 3 out of 9, which is then 1/3. So this will make, now for the second one to be soft, we'll have 6 out of 9, which is then 2/3. And for the soft one, for it to be hard, we then have 4 out of 9 because we've eaten one of them. We haven't eaten any of the hard ones. Then for the soft ones, we're left with 5 out of 9. Just keep in mind these should always add up to 1 as well. Okay. What is the probability that the first chocolate has a hard center and the second one a soft center? So first one has a hard one, which is this, then soft. So then we have 2 out of 5 times 2 out of 3, which is 4 out of 15. Calculate the probability. Actually, sorry, I should do this first. Probability of hard on the first one and soft on the second one. Okay, calculate the probability that either both chocolates have soft centers or both have hard centers. So we want the probability hard, and also soft and soft. So hard and hard is 2/5 times 1/3, and then soft and soft would be 3/5 times 5/9. So that should be 2 out of 15. Sorry, bell's really loud. 2 out of 15 plus 1/3, which then gives us 7 out of 15. Alright, there's 3 overweight people. I don't like this question personally. There's Ari, Barry, and Chris. And the chances of each person sticks to the diet are 0.6, 0.8, and 0.7 respectively. What is the probability that all 3 people stick to the diet? So first one, probability of A, intersection B, intersection C, because we want them all to stick to the diet, so it's 0.6 times 0.8 times 0.7. So it's 0.48 times 0.7, so 6. Oops, slight mistake. 0.336. Okay, so only Chris sticks to the diet. Now, be careful with this one. It says only Chris sticks to the diet, which means we want A not to stick to the diet, B not stick to the diet, and C sticking to the diet. So it's 0.4 times 0.2 times 0.7. So 0.06 times 0.7, 0.042. Alright. At least one of the 3 people stick to the diet. Now, because at least one of them, that includes A sticking to the diet, B sticking to the diet, C sticking to the diet, and then some combination of all 3 of them sticking to the diet. Quicker, if you work out, because remember they all have to add up to 1, the only scenario that this does not include is if none of them stick to the diet. So, because all of them have to add up to 1, we just do 1 minus all of them not sticking to the diet, which is 1 minus 0.4 times 0.2 times 0.3. 4 times 2 is 8, 8 times 3 is 24, so 1 minus 0.04 is 0.9876.